So last time we defined the notion of interactive proofs, okay? So that is a way for a prover to convince a verifier that, that an instance is in the language or not by using both interaction and randomness, okay? We saw a simple example for a concrete language, graph non-isomorphism. This example was interesting because without the use of interactive proofs, it's kind of unclear how a prover could convey that two graphs are non-isomorphic because there's nothing there's no short certificate that certifies that two graphs are not isomorphic in the general case. Okay, so that was showing that interactive proofs are at least useful for something, and then we saw kind of negative news that said that they cannot solve every possible problem. They have very specific limit on their powers, and specifically, we cannot use them to decide languages beyond P space. Okay. So what we're going to see today is perhaps one of the most fundamental tools in the theory of interactive proofs. It's called the Sumcheck Protocol. Okay, and we'll see how to use interactive proofs to solve problems related to counting, basically assignments to Boolean formulas. Okay, so let me try to motivate this problem briefly. So say that you're given a Boolean formula phi in say n variables with m clauses. Okay, and say that you're sitting here, right? You have phi in your hand, right? And you're wondering, is phi satisfiable? Okay. Now, by yourself, how much work is it going to take you? Exponential, specifically on the order of 2 to the n, right? So it's going to take you on the order of 2 to the n. In fact, well, we don't really know how long it's going to take you. We conjecture that it's going to take you as bad as 2 to the n. In fact, this is encapsulated in a complexity theoretic conjecture. It's called exponential time hypothesis that says that this is pretty much the best you can do by yourself. Okay, but now suppose a prover comes along. There he is, and he's willing to help you. So now you are sort of a verifier, okay? And you're still wondering whether the formula is satisfiable or not, okay? So how much work will it take you now? What could a prover tell you that is helpful? Satisfying assignment, for example, okay? So he could say, you know what? I think that this particular string of n bits is a satisfying assignment, right? And now it's going to take you time that is just polynomial in m and n. So for the particular problem of Boolean formula satisfiability, having a prover, even non-interactively, without any randomness, can give you an exponential speed up in work, okay? Now, suppose for a moment that you're actually interested in the complement of the problem. You're wondering whether the formula is unsatisfiable. So this is kind of analogous to when we switched from considering graph isomorphism to graph non-isomorphism, right? Now it's kind of unclear what the prover could send you to convince you, to help you, okay? And in fact, this question is strictly more general than graph non-isomorphism, right? Because if you kind of remember the way that certain part of the complexity landscape looks like, we have P, we have NP. NP is contained intersection of NP and coNP, right? Sort of SAT is a problem that is complete for NP. Unsat is a problem that is complete for coNP. And G and I is the problem that we looked at earlier. So we said, hey, there's something in coNP that probably is not in NP, right? For which we have an interactive proof, okay? Now, more generally, we could try to ask, okay, let's try to think about any unsatisfiability problem, such as, for example, the complete one for this class, unsat, okay? could it be that we can find some interactive proof that will help us? Right? Ideally, we would like to say, okay, we don't really know what to do interactively, but let's have a conversation and convince the verifier using an amount of resources and work that is only polynomial in M and N that a Boolean formula is unsatisfiable. Okay? Is it clear kind of the motivation? I think it's a really fundamental problem, right? Sort of satisfiability and unsatisfiability are really basic questions we ask about these computational problems about logic, right? And now we're kind of stepping up our sort of target, and we're going to ask, can we place all of coNP in the class IP, right? We could do that if we could find an interactive proof for the problem unsat. Okay? Are there questions about the motivation? I think it should also be clear that if we did succeed, which we will, I mean, otherwise we wouldn't be having this entire thing. It's rather surprising, okay? This means like everything in coNP, all kinds of unsatisfiability questions, we're going to have interactive proofs for. So the theorem we're going to prove today. Just a second. Yes?
Are there like theoretical reasons for why it's surprising? I mean, why it's surprising?
Well, true things are true. They're not neither surprising nor unsurprising, right? So now, in principle, what is surprising about this is that first, it is not about a specific language, right? It is encompassing a whole class, right? And maybe if you had only seen the interactive proof for GNI, you would think, yeah, GNI is kind of special. We had this nice structure of equivalence classes that behaves nicely under randomization, and so we could sort of plant this B to B and hide it between G0 and G1, depending upon whether they're isomorphic or not. And so it's a very special structure that comes together with graphs. But now when you move to general formulas, what do? Can you randomize a formula in a way that you can sort of secretly hide something inside? It's unclear what you would do, right? So, and indeed today, the interactive proof that we will see will look very different than the one that we've seen last time. So in this case, it's surprising because kind of Boolean formulas don't have this nice structure that we exploited last time. It's a good question. More questions? Okay, so that's the plan for today. We want to prove that this is the case, okay? And unlike last time, before we start using interactive proofs, we're going to have to add the structure that lets us use interactive proofs. So we're going to start moving away from the world of logic into the one of algebra. We want to kind of we want to translate this question, is a formula unsatisfiable, to some other question about objects that have sort of structure we can exploit in interactive proofs. Okay, so and today is going to be the sort of first time that we see a key sort of class of ideas that is used all over the place in the theory of probabilistic proof systems, something known as arithmetization. Okay, so again, it's a class of tools. It's not really formally defined. It's the best way to understand what it is to give example for that. So what we're going to do, we're going to take a 3CNF formula, again, that has n variables and m clauses. And we're going to map this object to a low-degree polynomial. Okay, P, that's going to have n variables. Okay, so let's look at an example of how we might want to do this. So let's say that I take a small example of 3CNF. Okay. By the way, a priori, it's not clear why we should be mapping anything to a polynomial, right? But as soon as let's say that we guess that we should, and we try to do that, then it will be very clear how we can translate this question into one that has a lot more structure. So let's just say for a moment that right now we really want to translate a 3CNF to a polynomial. Here's an example of a small 3CNF with 2 clauses and 4 variables. How could we write a polynomial that has something to do with it, right? Well, of course, we could just say, discard the formula and write some arbitrary polynomial, right? But that's not a very useful way to kind of transform our problem, right? So we want to somehow leverage the fact that, here's a clause, here's a clause, here's an and, right? What could we be doing here?
1 minus 1 minus x1 times 1 minus x2 times 1 minus x2.
Excellent. So that's you were suggesting how to translate this particular one. We'll get to that later because that's actually a pretty smart way of transforming it. Right now we can get by with an even simpler one. We're going to be mapping ors to pluses and ands to times. Okay, so I'm just going to write x1 plus x2 plus x3 times x4 plus, okay, we have a not here, so let's say 1 minus x2 plus x1. Okay. So I haven't really defined yet over what kind of algebraic structure we're taking these operations, but we will in a moment. The main point here is that we have this sort of simple observation that if a clause is satisfied, then the corresponding term is what? So if a clause is satisfied, what does it mean? That at least one literal is 1, right? What do I expect to see in the corresponding term? Something non-zero, in particular positive, right? Okay. If a clause is individually unsatisfied, then the corresponding term is what? Okay, good. So this is what happens to single clauses, but what we're interested in is what happens to the formula as a whole, right? So therefore, what we actually have, we can say the following. Consider any potential assignment, okay, of n bits. If it is the case that the assignment is satisfiable, then this polynomial that we construct, what value will it have? Yeah, non-zero, in particular positive, right? Because what does it mean for the formula to be satisfiable? It means that every single clause is satisfiable. We just agreed that whenever that happens, the corresponding term is greater than 0. Okay, when you multiply all these things, well, they will just even more greater than 0, right? Now, if instead this particular assignment is unsatisfiable, then the polynomial that we get out of it, oopsie, so there should be a's. So I'm looking at per assignment behavior, okay? The corresponding polynomial evaluated at this assignment, what will happen? It's 0, right? Because why is the formula unsatisfiable? Because somewhere there is a clause that is unsatisfiable, okay? That term will be 0. And in the products, if you have one term that is 0, then the entire thing is 0. Okay? Okay. All right, big deal. What's the point? In sum, what we can do is we have concluded that if phi is is not satisfiable, then we can actually write a way to summarize all of these conditions. Okay, we can say we can sum over all possible settings of the n variables. Okay, so consider all possible assignments. For each, evaluate the polynomial. Okay, and if the formula is unsatisfied, it means that there is no assignment that will make it happy. So you sum up all these values, you will get 0. Okay, and vice versa, because kind of everywhere on these assignments, the value of the formula and the polynomial kind of correspond to each other in terms of equaling 0 or being greater than 0, right? Okay, the point is that so this is a problem about logic, and now we have a problem about algebra. Not entirely clear why sort of a sum is particularly helpful right now, but we'll see in a moment a protocol that is able to deal with sums. Now, we still haven't made up our mind about what algebraic structure we're working over, and for that we need to think about what happens in a satisfiable case. Okay, so when the formula is unsatisfiable, it's pretty easy to understand what's happening here. You get 0, 0, 0, 0, 0, 0 everywhere, right? You sum them up, you get 0. If the formula has some satisfying assignments, this will be, some positive term. Okay, how big can this positive term be? How much? 2 to the n times what? Times what, sorry? 3 to the n. Yes. So why? Because, look, we're summing 2 to the n terms, right? Each one could have size at most 3 to the m. Why? Because in the worst case, every clause is satisfied by every literal, right? So we have 1 plus 1 plus 1, that's 3. Right? We have m clauses that get multiplied. We have 3 times 3 times 3. M times, so we have 3 to the m. Okay? Given that this is the case, now we have to make up our mind about where to work. Okay? And in order to do that, I'm going to tell you that sort of a factor we're going to be using is nice properties of polynomials over fields. Okay, and therefore we want to make sure that we work over a field. So the main factor we're going to be using, or other sort of useful algebraic tool, that we're going to use is that if f is a field, or let f be a field, and f is a polynomial of degree d, then the number of roots of f is at most d. Okay, we're going to be using this fact shortly. Now, because we want to work over fields, we need to somehow come back here and make sure we can state our problem to be 1 over fields. So given that I know that I have a control on how large this sum can be, what should I be doing to make sure that my problem is over a field? Yeah? I pick a large prime to work over that, right? So sort of these two things, again, it's not clear. I mean, I have to say, today's protocol was to some extent very surprising and revolutionary. It's not obvious where to go and why. So I think graph non-isomorphism is a really cute protocol. Whatever we see today, the Sumcheck Protocol, it's a beautiful protocol, but it's it requires some sort of leap. Okay. So right now I'm just promising you that we're going to need this. Okay, and therefore this dictates some decisions. Okay. Given that the sum is at most this much, and given that I'm telling you right now that we want to work over fields, what we want to do, we're going to pick a prime q greater than 2 to the n times 3m, and we'll do all arithmetic over the field FQ. Okay? Yes?
I don't know if this is very important, but you could save a little bit, right, in the sum that more, because instead of, like, in the OR, you could do, maybe this is what you suggested earlier.
Yeah, so I can make it a bit smaller, and this will come back later. Right now, it doesn't really make such a big difference, because if Q is this big or this other big, anyways, working modulo Q means that as a verifier, I experience log Q as cost, right? So this will mean that discussing things about FQ elements will cost me poly M and N, okay? Which is fine, right? That was my kind of target. All right, so okay, so we have now decided that we're working over FQ. So this is all in FQ. And what we've basically done now is we've done the arithmetization. We have translated our problem about logic. Now we have a problem about algebra. And now the verifier's goal is that he has this polynomial at hand. He can evaluate it anywhere, really, he wants, right? Because I've just syntactically transformed the Boolean formula into a formal polynomial. I can evaluate this polynomial anywhere I want in polynomial time, right? And what I would like to be convinced of is is it indeed the case that if I sum this polynomial over the Boolean hypercube, I get 0, okay? If I do, then I'm convinced the original formula was unsatisfied. If I don't, if I get some other thing, it wasn't, okay? Good. So now the verifier has a new goal, which is be convinced that the sum of this polynomial over the Boolean hypercube is 0. Okay. So now let's discuss a protocol for doing precisely that. Okay? Okay. So let's discuss, it's called the Sumcheck Protocol. Why is it called Sumcheck? Because we're checking the sum of polynomials, right? So actually it's a pretty good name. Not to be confused with checksums, which show up in the theory of linear error correcting codes, right? All right, so we have the prover. We have the verifier. Both of them have as a common input P. And they have to start doing something, right? So anyway, some of you might have seen this protocol. So many of us have seen this protocol actually many times. So it's kind of it kind of feels obvious how you start, but so this protocol is actually non-trivial. So any thoughts about what we should be doing here? So remember, 2 to the n is a large number, right? In particular, it is more than poly n, right? We have to we have to help the verifier, okay? Yeah.
Fix the first variable and ask the prover to send a polynomial that's the sum over x to the xn.
Yeah, so the idea of the Sumcheck protocol is to proceed variable by variable, okay? We're going to try to reduce from one round to the next a Sumcheck problem over n variables to a Sumcheck problem over n minus 1 variables. We do this n times, we'll be left with a Sumcheck problem over one variable, which is easy, right? Because it's just summing a univariate polynomial over 0 and 1, right? It's a very tiny hypercube because it has dimension 1, right? So that's what we're going to do. So let me write down the protocol, then we can sort of analyze it. What the prover does, he computes a so-called partial sum. It is a univariate polynomial which is defined by summing over everything but the first variable. So you take p, you leave x1 free, and you kind of sum over the rest. This polynomial, what is the degree of this polynomial? In the particular case here, yeah, m. The point is that it is the individual degree of p. Right? P is a multivariate polynomial. It has an individual degree. Okay, this individual degree is not huge in our application here, right? Because this polynomial p, I forgot to mention, also has a degree that is not big, right? It's small. It's polynomial. In particular, it's n. Therefore, it is a polynomial that it is okay to send. So the prover, in its first message, will say, hey, here is the first partial sum. The verifier receives it, okay? And maybe the verifier should check something about P1. So there is a property it should satisfy. If really it is the partial sum, what it should check the verifier about P1? Yeah, exactly. So the verifier says, okay, thank you. I might as well check that indeed P1 at 0 and P1 at 1 actually equals 0. Why? Because we summed over everything but the last variable. If we do sum over the last variable, which is what this achieves, I expect to get 0. Okay? So if that's not the case, the verifier rejects right away. Okay, but we haven't made much progress. What the verifier does now, it will sample a random field element, okay? And it will send it back to the prover, okay? Now, what the prover is supposed to do is it will fix the first variable to this value and sum over the rest, leaving the second variable free. Okay, so here it is. P2 of x is the sum over A3 up to AN. P, now in the first slot, I put R1, x, and then I continue from A3 to AN. Okay, and now the prover will send back P2 of x. Okay, now comes maybe the first sort of a non-trivial step. What should the verifier check about P2? Allegedly, P2 is this thing, right? What should it be checking, the verifier? Yeah?
P2 of 0 plus P2 of 1 is equal to P1 of R1?
Yeah. So it will check that P2 of 0 plus P2 of 1 equals P1 of R1. Why is that? Well, if P1 really was that partial sum, right, which we checked, right? This particular test is not probabilistic, it's deterministic, but that's all right, okay? So we checked it. At this point, you can think about P2 as basically taking P1 evaluated at R and further splitting it into two subsums, right? So this is what I should be checking. Does that make sense? No, let's do another round. But anyway, we'll analyze this very carefully in a moment because the protocol is at once intuitive and confusing. Okay, so it's going to sample R2, send it. Here's R2, and the prover will compute P3, which is the third partial sum. It will go from A4 to AN. So P will have two variables fixed to R1, R2, then X, then A4 through AN. There is the reply from the prover. And what will it check? it will check that P3 at 0 plus P3 at 1 equals P2 over 2. Is the intuition clear? I'm sure if everybody can see. All right, so it continues like this. Okay? And at some point, the prover will send Pn of x, okay? And it will check that Pn of 0 plus Pn of 1 equals Pn minus 1 at Rn minus 1, okay? It will send back Rn. This is mostly like a, to make the syntax nice, but it doesn't really have to send it. And the last check, what should the last check be? Notice, by the way, that we haven't touched P at all so far. So I need to check that P at R1 through Rn equals Pn of Rn. So this is the first and last time that the verifier actually touches P. Okay? So notice that somehow so let me also define what is Pn here. So it's there. Pn of x is some, not now. It's P of R1 through Rn minus 1 x. Notice that the Sumcheck protocol has two hooks to ground truth. There is the ground truth of the sum that you care about at the very beginning, right? And at the very end, you touch the polynomial that you care about. Okay? And you're kind of these are sort of probabilistic reductions that sort of connect the beginning and the end of the protocol. Now, let's make some sort of simple remarks about it. Also, I want to highlight in a different color where sort of truth comes in, which is here and here. Okay, there are two places that there are things that they're trusted. So here is checking that sum over P equals 0. Okay, so the 0 plays in here and P plays in here. So let's make sure that we agree on the efficiency of this protocol. So in terms of parameters of P, what is the running time of the verifier? It's polynomial in what? So it's polynomial definitely in n. Why? Because if we have n variables, we're doing n rounds, right? So clearly I'm doing work n. In each round, I'm paying the individual degree of P. So it's also polynomial in degree of P. Okay. And also I need to evaluate P once, right? I need to be able to evaluate it somewhere. Okay. So I'll just write, size of P. Okay. In the particular case where we want to use it, all of that is fine, right? Because the degree, we established that it is m, right? And the cost to evaluate the polynomial is basically linear in the size of the formula, right? Because I have syntactically transformed the formula by basically replacing ors with pluses, ands with times, negations with 1 minus, right? So I can definitely evaluate the formula in time that is linear in the formula size. So I'm not really paying anything more than polynomial in whatever I had. So that's all right. So this is good, okay? So for this to be an interactive proof, we need to have two properties. What are the two properties? Completeness and soundness. And remember that you should always first check completeness before soundness. Not because maybe it's not complete, but just because it sort of helps you go through the motions of being familiar with the protocol you just wrote, right? So completeness means that we want to say that if indeed sum over P, the sum over the polynomial over the polynomial over the Boolean hypercube is 0, then the probability that P and V equals 1 is 1, right? And first, remember that the completeness is only for the prescribed prover, right? So if the prover does weird things, then clearly we're not supposed to have any guarantees, right? When we say completeness, we're saying for the honest verifier and the honest prover strategy, the one that does what the protocol specification says, okay? We want the verifier to accept. Other questions about at least why everything goes well if the prover follows the prescribed strategy. Is it clear why the verifier always accepts? Right? We have this big sum, we're splitting it, then we fix a variable, then we're splitting, we fix a variable, and if the prover continues following this strategy, then all of these checks always pass regardless of the choice of the various random elements. Okay? That's good? All right. Now for soundness, this is where we actually have to say something. What we want to say is that if the sum of the polynomial is not 0, what we want to say is that then P is overloaded. Let me change that. So P is both the polynomial and the prover. That's not good. Let's say prover. So then, regardless of what prover I consider potentially computational unbounded, we want to say that the probability that this prover interacts with the verifier and makes him accept is bounded, okay? Not large. In this particular case, we'll show that it is n times the degree of P over Q, okay? The size of the field. We're going to show this is the case. Okay? Again, always remember that here we have a quantifier. We have to be able to show that the verifier is safe regardless of what the prover does. Okay? All right. So now let's prove that. So does anybody want to attempt a high-level intuition at arguing the proof? Or at least a proof strategy. What proof strategy are we going to take? Yeah? Well, sure. I mean, we're going to have, at some point I said, this is going to come in useful. So we will use this, which is basically Schwarzschild. But just take a step back for a moment. So we have this rather complex protocol. It has n rounds, right? So we can't just start, right? We need to have a plan. Yeah?
In the last step, we know that the prover must send the correct, right? Because
it depends, right? Maybe he got lucky in the middle, right? I didn't catch him, so in the last step, it's okay, right?
maybe by induction.
Yeah, so what I really wanted to hear was induction, right? So this protocol, is a recursive protocol, right? Because even though I didn't phrase it like that, by the time you're here, you have a Sumcheck protocol over n-1 things and over n-2, right? So given the structure, it seems only reasonable to try to attack the analysis by way of induction, okay? So because of this, what we're going to do is we're going to try to define n events, okay? The events determine basically if at a particular round the prover lies. Okay? At any round, there is a prescribed a prescribed polynomial that the prover has to send. Okay? So at that round, either he sends it or he doesn't. Okay? So we're going to define events that determine whether he does or he doesn't. And then we're going to try to make our way towards bounding the probability that he wins in terms of these events. Okay? For example, if he lies right away, then we catch him with probability 1. So let's at least, for example, prove that first using the language of the events that we introduced just to get familiar with them. Okay? So we're going to define EI. Okay? Is the event that P tilde I, so P tilde I, I'm going to use it to denote it, the polynomial that is sent by the prover in the ith round equals pix, which is the correct polynomial to send, right? Notice that regardless of what p sums to, pi is well defined. It's just the correct partial sum. Okay, so let me write it. It's a sum from ai plus 1 through an. P, I put in r1 through ri minus 1, x, then ai plus 1 through an. Okay, so that's an event. Another event that we're going to define is w, which is the event that a prover wins. Now, both of these events are defined over a probability space. The probability space is the randomness of the verifier, which consists of R1 through Rn. Okay? All right, so let's try to do the stupid simple claim first. We're going to say that the probability that the prover wins if the prover never tries to lie is what? So 0, right? So this is a rather lousy prover strategy that, despite knowing that he's proving a false claim, he actually goes ahead and sends exactly what the protocol tells him to do. Okay? So what's the proof? Well, this quantity is certainly bounded from above by the probability that the prover wins and he doesn't lie in the first round, right? Which is 0, right? Because P1 tilde at 0 plus P1 tilde at 1, which under the assumption of event E1 actually equals P1 0 plus P1 1, is not 0 because we are in the soundness case. Okay? But I'm doing this slowly because you should see these things once, and then other times we'll go over these things a little bit more, sort of with more speed. But the first time it's good to see these things properly. Okay, do we agree with this? This is kind of the simple case. This is saying that at the very beginning, if you don't lie, and in particular if you don't lie anywhere, then you're going to get caught right away. All right. So, and now I really want a little bit more space, but I can't continue this way. So I will get it here. All right, the next claim we're going to prove is that the probability that the prover wins, which is the event we care about, is at most n times degree of p over q plus the probability that the prover wins given that he never lies, which we have already established is 0. Okay? Right, so that's 0. Right, so then we would be done. So let's prove this statement by induction. Okay? We'll show that for every j in n, the probability that w is at most, make sure I get the indices right, n minus j plus 1 degree of p over q plus probability that he doesn't lie starting from the jth round. Okay? So right now we're considering, suppose that the first time he lies is at ej. So the last time he lies was at ej minus 1, and from then onward it is always honest. Okay? Now clearly when I set j to equal 1, then we get what we want, right? So it suffices to prove this is the case. Okay? Now, let's look at the base case, which is when j equals n. Okay? So the probability that, so basically what am I looking at? I'm looking at the very end, right? At the very end, either he lies or he doesn't, right? So the probability that he wins is at most the probability that he wins given that he doesn't lie, or he does lie, or that he doesn't lie, right? Okay, so we're at the very end. Okay, we have two cases. This is kind of the case that we're going to grow via induction, so we're not really worried about it. So let's look at this one. Okay, so this is a simple event. This is saying that something happened. At the very end, he lies. Okay, so he's not sending the correct polynomial. We don't care what happened in the past. Okay, at the very last round, he's not sending the correct polynomial. What is his probability? Remember, don't get caught up about what he did before. We define these events we always tied to either the correct polynomial or not the correct polynomial. If in the last round he sends something anything other than specifically p with r1 through r minus 1 in the first coordinates and x, what will happen? Yeah, so if he's not sending this polynomial, he's sending anything other than p evaluated in this way, and then what's actually happening in the last round? Let's just see the syntax. Right, so he's sending some other polynomial, univariate polynomial, and we're checking it against p, right? We shouldn't really be thinking about p as a multivariate polynomial. We have already fixed r1 through r minus 1. But there is a free variable, the last one, right? And now, if he's not sending the correct polynomial, now we have two univariate polynomials that are distinct, okay? And we're testing them at a random point of whether they agree, okay? Now, because of this fact, okay, these two polynomials cannot agree on more than a number of roots, okay, which is bounded number of degree, by the degree, okay? So we know that this is at most the degree of p over q plus this thing. All right, so I have to make sure that we're together here, though. Do people agree with this? Okay, so we're at the end. It doesn't matter what is r1 through r minus 1. What's happening is that the prover decides on a polynomial Pn to send. Rn doesn't exist yet, is it? So Pn is independent of it. So it's kind of, Pn has been written down. There is the correct polynomial he should have sent. P with r1 through rn minus 1 fixed, okay? If it doesn't send that one, now we're comparing two univariate polynomials that are distinct at a random point, okay? They will evaluate to the same point only in at most number of roots locations, okay? So we'll catch them, provided that q is sufficiently bigger than the degree. Are we together? And it's important to understand this part. Are there questions about it? Okay, so that's the base case. The inductive step is basically the same thing, okay? But we're doing it sort of in the middle of the protocol. So let's just say that the probability that the prover wins is at most by induction n minus j plus 1 degree of p over q plus the probability that the prover wins, given that he didn't lie yeah, I guess I'm off by 1, so I'll be proving. Okay. So now we're going one step further, okay? So now this is equal to this same expression. And now I want to sort of split this event according to what he did in the round prior to that, right? Because right now we understood the last round. We're trying to make our way to the first round. So suppose that we did make it to the jth round. Let's go to the round before it. So I can split this event according to what happens on ej minus 1, right? Either he was honest, or he wasn't. Right? Actually, let me put maybe this one over here. And maybe I should put a less than or equal here. There we go. Right, so this is my inductive hypothesis. So I haven't really done anything. Now I take this event and I look at, okay, what happened in the round before? So what can I say? So what should I be saying? Yeah.
Probably complement EG minus 1, and everything else after that is still like at most a degree of P over Q.
Right. Now notice that it's crucial to know that I didn't lie in the following round, right? Because otherwise I wouldn't be able to claim that by lying in the j minus 1th round, I actually compared two polynomials that are distinct, okay? I need to know that in the following round, he did say the correct thing, okay? It's because of this discrepancy that we did use implicitly here, right? So here he was saying, where do you go? He was saying something false, right? And it's not so much that it's false, but it's different from the truth, okay? And we knew what the truth was. We knew what the truth was because we had P, right? But now somewhere in the middle of the protocol, the prover is in charge about what he told me, right? So I'm actually comparing, whatever he sends here to the next one, right? So it's important to know that that's correct, okay? So that I can claim that the two polynomials are distinct, okay? That's why I can't just zoom in the middle of the protocol and say that, oh, because you lied somewhere else, then I have to catch you here. No, that's not necessarily the case, right? Maybe he lied somewhere else, now he's being consistent with his lie in the middle of the protocol, right? And I'll catch him later on, right?
And this is why you need like interaction, right? This is why the verifier is not just picking n r's and sending them to the prover.
Yeah, that would be insane, right? So it's important in each of these rounds that the polynomial that is chosen by the prover is independent of the randomness on which is being tested later, right? Otherwise, if you send all the randomness in advance, okay, he can just craft all these polynomials they happen to pass the tests, okay? By the way, that's actually maybe like a good exercise to try to do, to try to break the protocol by crafting sort of a malicious set of partial sums that depends on the randomness of the verifier. Okay, but so the point is that this is at most n minus j plus 1 degree p over q plus this expression is at most degree p over q because we're comparing distinct polynomials, and then we continue with the other part, and this proves the inductive step, right? So because now these two guys combine and we made progress, right? So we have n minus j plus I think 2 or whatever. Oh, maybe one way to write it is like this: n minus j minus 1 plus 1 degree of p over q, right? And we're making progress from j equals n to j equals 1, okay? Look, I know it's a lot of formalism, but this is a confusing protocol, and I could stand in front of it and tell you, all these conditional events, and I'll confuse you, right? But I think, this is, a formal proof, okay? And so you can try to go through it again and make sure that you understand it. This is a very intuitive protocol that analyzing it formally is actually rather confusing. Questions? Yes?
What is the intuition time? I mean, I get the proof, but what I can't get here.
The high-level intuition is that what you want to do is you want to force the prover to lie at some point, right? So he has this big sum he wants to convince you of, right? And you're trying to say, okay, if you really know the big sum, then please tell me about partial sums, right? So he could start off by lying right away with some polynomial that happens to sum to 0, right? That has nothing to do with p. Right? You can say, yeah, I really can't lie at the beginning, so let me send you some other polynomial that just sums to 0 if you just fix if you sum it on 0 and 1, and I'll at least get past the first round. And then, each time he can either take the chance to be consistent with itself so that it will pass for all r's, right? Or switch to some other polynomial, in which case I will catch him with high probability. Okay, if he's sort of is a bit of a coward, then he will continue being consistent with himself, but because he lied at the very beginning, at the very end I'll check it against the actual polynomial, right?
The point is that the prover needs to be consistent with himself.
Yeah, so either he's consistent with himself until the very end, or he sort of becomes inconsistent at some intermediate round, okay, and I'll catch him then, okay? Now, to make this formal, actually what you need to look at is the last time he didn't lie, right? Because you want to compare the last lie with the first sort of truth to make that comparison, okay? Does it help? More questions? Yeah?
I'm a bit confused on if he switches, how do you catch him on that? Because even if it's based on the last evaluation and the current one, wouldn't both evaluate correctly and it still work out?
The point that's kind of the point is you want to look at the last time he lies, because the last time he lies, the next time he didn't lie. So now you know that the two polynomials are different, and so you will catch him there. Because just lying is not good enough, right? You actually need to know that you're checking him on two different polynomials. You definitely do that at the very end, in the event that he didn't lie at the beginning, right? But otherwise, you don't know in the middle, so you kind of start from the end, and you say, okay, look, either you sent me the correct thing at the very end, if not, I catch you there. If you did send me the correct thing, okay, let's go back one round. Did you send me the correct thing there? If yes, okay, let's keep going back. At some point, either I hit the beginning, and then I know you definitely were stupid, right, because I catch you right away, or you lied somewhere, and I'll catch you with high probability. Okay, so you want to analyze from the bottom up. Okay, you will get really confused if you start from the beginning. Okay, you want to start going bottom up. Okay, it's a beautiful protocol, very influential. It shows up all over the place in interactive proofs. Now, let me just make sure that I'm precise about how the whole protocol goes, because this is a subroutine, right? Where we started with a problem about unsatisfiability of Boolean formulas. So how is this subroutine actually used? It's simple, but I just want to make it explicit. You have a prover who became blue. You have a prover and a verifier. Their common input is a Boolean formula, right? That's the problem we started with. What the prover will do, it will pick a prime q such that q is bigger than 2 to the n times 3 to the m. It will send q to the verifier. Q will check whether it's actually a prime. It can do it even probabilistically. It doesn't even have to use a deterministic test for it. It just needs to be like a good enough test. Okay. If it does so, then sort of both of them map phi to p. Okay. What does it mean? It means that they both of them write in their head an arithmetic circuit that evaluates the polynomial p. Right. Notice that you cannot write the polynomial p formally, right? That will be many, many, many terms. What you want is write down a representation for it that lets you evaluate it. That's an arithmetic circuit, right? And then now they invoke as a subroutine the Sumcheck protocol. They're gonna run Sumcheck on the claim sum of p equals 0. Okay, and sort of this is a subroutine that we just looked at. Okay, so yeah, this is just to complete the interactive proof. Does it make sense? Notice that there was a sort of a reduction here where we moved from the problem about phi to a problem about polynomials. Okay, arithmetizations and these types of reductions will show up all the time in this class, okay? And that sometimes it will be much less simple than the one that we see here, okay? By the way, it's worth noting that you may wonder, why are we specifically using fields? Polynomials are just as well defined over rings, right? Yes, you had that question. No, yeah, I was making a point, maybe. Okay, go ahead.
Sorry, I was concentrating on that.
Yeah.
So this is not this is public coin protocol, right?
So we haven't really talked about this, but let me highlight it since you ask, right?
I just saw on the website when you wrote the GNI, it was private coin.
Yeah, so let me make that point. Last time we saw a protocol for GNI. How did it work? The verifier first sampled B, then samples a random permutation and produces this H, which is pi of GB, right? When the two graphs are isomorphic, H carries no information about B. That's why the prover is confused. Thinking about that protocol, you'll be led to believe that the power of the verifier lies in the fact that the verifier knows B and the prover doesn't. Okay? So this notion is called private coin interactive proof. We will have an entire lecture dedicated to these things. And you might wonder, maybe that's private coins are very powerful. Yet, here's a protocol where there is no such feature. Every time the verifier generates some randomness, what he does is it sends it in full to the prover. So there's no secret anytime. All that's being used is sort of chronological, is just causality, right? Sort of things that happen later, things that happen earlier cannot be dependent on things that happen later, okay? That's all we're really using here. This is a called public coin protocol. And because Boolean unsatisfiability is complete for coNP, this actually implies a protocol also for GNI, okay? Because you can write down a formula whose unsatisfiability encodes GNI problems. It does have more rounds, so there's a question about what's the correct round complexity, for example, for public coin protocols for GNI, and we'll answer that question in a couple of lectures. Okay.
So is there any shorter
There is a I think 2 or 3 round public coin protocol for GNI. And in general, the sort of the question of round complexity of interactive proofs is something that continues to be like a problem of interest to researchers, and so I'll mention more about that in other lectures. As I was saying, you might be wondering, why specifically are we using a field when polynomials are just as well defined over rings, right? So typically, you can define polynomials over rings. The point is that this useful fact that we can tie the number of roots of a polynomial to the degree specifically comes up when you consider f of x, where f is a field, because this is a unique factorization domain. to see an example where that doesn't hold, so let me just kind of say that does not hold over R of x for a ring R. And so here's an example where you have a low degree polynomial that has more roots than it should. Okay? So fix the ring Z mod 12Z. So here I'm taking modulo 12, which is definitely not a prime. And I can look at the polynomial x squared minus 4. Okay? So can anybody factor this one for me? Right, so it's x minus 2 and x plus 2. Okay, that's one factorization. So clearly it vanishes at 2 and minus 2, right? Can anybody factor it in a different way for me? Like less obvious. Okay, so it's actually, we can do x minus 8 and x minus 10. Notice that 2 is different on 8, modulo 12, okay, and minus 2 is different on, oh no, they're actually the same, but it depends that there are three roots as opposed to 2. Let's check at least that 8 is a root, okay? 8 squared at 64, minus 4 at 60, okay, divided by 5, we get 12, right? So that definitely is a root. So here you have a polynomial that has degree 2, yet it has 3 roots, okay? So that's why it's important that we pick a modulus that is a prime, because we were working over a field as opposed to a ring. Okay. All right. So, this is a very useful protocol. And now we're going to show how it immediately implies something much stronger than the inclusion coNP in IP. Actually, it gives us much more than we kind of bargained for. Okay. So I'm going to erase this board.
Is there a protocol for Sumcheck with smaller number of rounds?
These are great questions, and we didn't know of things like that until about, let's say, a couple of years ago. So again, reducing round complexity of interactive proofs is what languages have interactive proofs with a small number of rounds is it's an open research frontier. We know things that are sort of much more sophisticated than this one, but yeah. So let me make some remarks that will let us go beyond just unsatisfiability. We're going to look at counting problems. You know, like counting problems, problems that involve counting, right? So in particular, there is this problem called sharp SAT, which says, given phi, how many assignments satisfy phi? Okay? Notice that this problem is strictly harder than either satisfiability or unsatisfiability, right? Because if the answer is 0, then it means it's satisfiable. If the answer is some number greater than 0, then it means that it's satisfiable, right? We can actually design an interactive proof for sharp SAT. Okay? And this goes back to the arithmetization that was proposed at the beginning of class, okay? Which is different from the arithmetization that I raised earlier, that lets us actually do a reduction, okay, to sharp SAT. Okay, so here's a different way where we can arithmetize a clause. So let's say that we have x or y or z naught. We can actually map this, instead of saying x plus y plus 1 minus z, what we're going to consider is 1 minus x, 1 minus y times z. This particular transformation is remarkable in that it exactly preserves the value of the clause. When this one is satisfiable, it means that there exists one of the literals that is 1, then this will be evaluated to 1. Conversely, if this one is unsatisfiable, namely all of the literals are 0, then this one will be 0. Okay? So if you do this transformation with the above, what we have is that for every a1 through an in 0, 1, we actually have that phi of a1 through an literally equals p of a1 through an, or yeah, it's not the p of before, this is a new p, right? So rather than being that it's either 0 or greater than 0, we actually we're matching exactly the value. Therefore, what we have is that sharp the number of satisfying assignments to phi exactly equals the sum of this polynomial over the Boolean hypercube. Right? Okay, but we can just use the sum check. What's the change? So if, say, we want to construct an interactive proof for sharp sat, what would we do now? So first, so instead of being p, it's blue p, right? So it's going to be a different p. Now my bound here is going to be some other bound. I need to also derive it, right? So what the bound? Yeah. Yeah, 2 to the n times. Oh, that's enough, right? So. Yeah, it's enough. Because we are preserving exactly the value, so it's either 0 or 1, so it's 2 to the n. So instead of having the black bound, we have the blue bound, right? And then I run the sum check on a blue p, right? And instead of putting 0, what do I put here? Just whatever they claim to be, right? Some value v, right? And otherwise, I just do exactly the same protocol. Because remember here, in this protocol, there's nothing special about the fact that this is 0. Okay? It's just some claimed value for the sum. Right? And I just run the same protocol. Now, this seemingly sort of a minor change actually tells us the interactive proofs are a lot more powerful than we have shown so far. Because sharp sat is complete for a class of problems called sharp p. This is the problem where I give you a non-deterministic Turing machine and I ask you how many accepting paths are there for the non-deterministic Turing machine. And this problem is these type of problems are very, very hard. So in particular, there's a theorem called Totus Theorem that says that the entire polynomial hierarchy can be solved using counting problems. Okay? And we have just basically shown that the class IP contains p to the sharp p. Now, what are these problems? These are problems such as, is it the case that for all x1 there exists x2, for all x3 there exists x, and I continue to ask whether there is a sort of the formula is satisfiable or not, right? Because sort of if you can think about it, okay, if you haven't seen the polynomial hierarchy, it doesn't really make too much sense. But basically, NP says, does there exist an assignment that makes the formula satisfied, right? coNP says, is it the case that for all assignments, the formula is unsatisfiable? Notice that these are kind of two different quantifiers that exist and for all. The polynomial hierarchy considers such problems where you alternate these things, some polynomial number of times. Okay? And, kind of coNP is like way down, okay? So this is a very surprising containment, okay? So what we've learned is that with the power of interactive proofs, not only we can solve questions that are, at the end of the day, rather simple, like unsatisfiability, but we can actually solve all counting problems, okay, which are much harder. Again, it's kind of hard to appreciate how hard they are if you haven't sort of done some complexity theory at those levels up there. And actually, the story doesn't end here. What we will do next time is we will build on this understanding. And actually, we will not be using the Sumcheck protocol anymore, but we will learn from it to come up with some other public coin protocol, okay? That kind of is reminiscent of it. In particular, historically, it came immediately after, okay? When the Sumcheck protocol was discovered, there was soon after another protocol called Shamir's protocol, after its inventor Adi Shamir, that actually shows the tight inclusion that we're aiming for. This shows that P space is contained in IP. Okay, so that actually with interactive proofs, you can decide all languages that are decidable in polynomial space. Okay, which is an enormous class. Oh wait, I think that's all I have for today. There's a question. Yeah.
So what do you mean by P to the P? What does that notation mean?
So this means that you have a polynomial time Turing machine that has an oracle that is able to solve sharp P problems. So for example, it's like writing an algorithm where you can call a subroutine to a magical box that you can pass it counting problems and it will solve them for you for free. Okay? In particular, you can call this box like a few times or once, or you can use it to just solve one counting problem, or you can do more things. Okay? So if you're not familiar with sort of this type of notation, I think it's good to look it up in Aurora Barak. Yeah. All right. That's the end of class.